Hey there, and welcome to this explainer. Today, we're going to dive straight into a completely invisible, highly technical money drain that is secretly hitting industrial electricity bills all over the world. We're going to visualize some hidden electrical physics that dictate how power is actually consumed, and honestly, more importantly, how it's completely wasted.
So picture this. You've got a factory boss who's just fuming and also deeply confused. He just opened the company's electricity bill and got hit with a massive penalty charge for something called reactive power. I mean, what even is that? Well, today we're going to act as engineering detectives. We're going to find out exactly what this invisible force is, why the power company is so absolutely furious about it, and how a clever electrical engineer can actually fix it.
Here's our roadmap to crack this case. We'll start with the mystery charge, then look at AC supply versus DC power. After that, we'll be decoding the power triangle, seeing how inductive loads cause lag, figuring out correcting the power factor, and finally, protecting the grid.
All right, let's jump into Section 1, the mystery charge. We need to figure out where this penalty actually applies.
Okay, so the first clue in our mystery is that this fee, it doesn't actually affect standard residential consumers. You're never going to see a reactive power penalty on your home electricity bill, and it doesn't apply to simple DC circuits either. It specifically targets massive industrial sites running heavy AC equipment. We're talking large three-phase motors. To understand why these massive sites are getting penalized, we really have to look closely at the power supply itself.
Which brings us to Section 2, AC supply versus DC power. To figure out why AC circuits are so heavily monitored and fined, we need to quickly shrink down and look at how the electrical current actually behaves inside the wire.
In a standard DC circuit, power factor simply isn't an issue, right? Because the flow of voltage and current is totally constant. It's a one-way street. But when we look at AC power through an oscilloscope, we see it has this sine wave pattern. The voltage and current are constantly changing. They're rising, falling, and alternating direction 50 or 60 times a second. And because of this constantly changing intensity, the timing of the voltage and the current waves is absolutely everything.
Now here's where it gets kind of wild. The total power supplied to the factory, which we call apparent power, isn't necessarily the power actually being used to do useful work. Because the AC waves are constantly rising and falling all the way to zero, we take an average, called the root mean squared, or RMS. If we multiply the RMS voltage and current being supplied, we get apparent power, measured in volt-amperes. This tells us what is being delivered, sure, but it hides a super costly secret about what is actually being used. Let's uncover that secret in Section 3, decoding the power triangle. If the power supplied isn't all being used, where exactly is it going? Well, when we hook an oscilloscope up to the factory's load, we see that the current is actually delayed. It's lagging behind the voltage. To make sense of this, we need to translate this delay into geometry.
By plotting these power values out as lines, we form a power triangle. The horizontal line represents real power, measured in watts. This is the energy actually doing the physical work, like, turning a shaft. The angled line is our apparent power, the total power we calculated earlier. The angle between them, that represents the exact time delay between the voltage and current waves we saw on the oscilloscope. And that vertical gap connecting them at the end, that is our missing energy.
So the absolutely crucial point here is that this vertical gap is called reactive power. It's measured in volt-amperes reactive, or VAR. And guys, this is energy that isn't doing any useful work at all. It is literally just flowing back and forth in the circuit, sloshing around and taking up space in the wires. The power company has to supply it, the factory's wires have to carry it, but it produces zero productive output. And this right here, is exactly what the power company is penalizing the factory for.
Let's move on to Section 4. Inductive loads cause lag. To find the specific piece of hardware causing this delay in the current, we have to evaluate the different types of components drawing power on the factory floor.
And this brilliantly illustrates the real culprit. While purely resistive loads, like an old incandescent light bulb, keep voltage and current in perfect phase, inductive loads, like massive electric motors, inherently cause the current to fall behind the voltage. And because industrial factories are absolutely packed with enormous electric motors, their entire system just begins to lag. But why does a motor actually do this? Well, it all comes down to magnetic fields. As AC power flows into the motor, it builds a magnetic field around the coils to create rotation. But as the AC wave naturally falls, that magnetic field collapses. That changing magnetic field actually induces its own voltage, and that pushes back against the applied voltage from the grid.
This pushback physically delays the current from flowing, causing it to lag by up to 90 degrees. So as the magnetic field constantly builds and collapses, that reactive energy just gets shoved backward and forward into the wires instead of turning the motor shaft.
So, let's look at Section 5, correcting the power factor. How does our clever electrical engineer actually fix this massive money drain and get the angry factory boss off his back? Well, he has to correct the power factor.
Power factor is simply the ratio of real power to apparent power. A perfect score is a 1, meaning every single volt-ampere supplied is doing useful work and the voltage and current are perfectly aligned. But because a perfect 1 is incredibly hard to achieve in a real messy factory setting, engineers typically aim for a power factor of around 0.95. Hitting this number effectively eliminates those utility penalties.
To build our solution, we have to revisit our components. If you remember earlier, we noted that capacitive loads do the exact opposite of inductive loads. While motors cause the current to lag, capacitors store energy in an electric field and actually cause the current to lead the voltage. So by precisely calculating the amount of reactive power the motor is producing, engineers can install a specifically sized capacitor right next to the motor, wired in parallel. This creates what I like to call an elegant dance of physics. The real power output of the motor remains completely identical. But now, that useless reactive power, it doesn't travel all the way back through the factory's grid to the power plant. Instead, it just bounces harmlessly back and forth between the motor's magnetic field and the capacitor's electric field. Because this wasted energy is contained locally, the overall apparent power drops, and the total current drawn from the main grid is drastically reduced. Bam! The penalty is gone.
Finally, let's wrap up with Section 6, protecting the power grid. Now, you might be wondering, if it's just energy bouncing around locally, why does the power company care enough to heavily fine the factory in the first place?
It all comes down to scale and hard infrastructure limits. Grid equipment, we're talking multi-million-dollar generators and transformers, are rated for total apparent power, not just the real power being used. If thousands of factories have bad power factors, they fill the main transmission lines with useless reactive power. This physically consumes the grid's spare capacity, meaning literally no new homes or businesses can be connected. Plus, the extra current generates huge heat losses in the wires. Ultimately, this forces utility companies to spend billions upgrading their infrastructure to much larger sizes just to handle bouncing, useless energy. So, rather than eating the cost, they pass those billions directly back to the offenders through massive penalty fees. Makes sense, right?
By simply applying opposing physics to balance the electrical load, engineers literally save millions in wasted grid capacity and keep our global power infrastructure from buckling under the weight of useless energy. It is just a brilliant hidden fix. And, it leaves us to ask what hidden bouncing inefficiencies might be secretly taxing your own everyday systems. Thanks for joining me on this explainer, and I'll catch you on the next one.